Okay, physical science time. Today we are talking about thermal energy. For the last couple of weeks, we have talked about thermal energy, but today we are talking specifically and more in detail about thermal energy. In what context did we talk about thermal energy previously?
Probably friction.
Friction. Thermal energy, remember, is the one of the ways that thermal energy can come about. B is from friction. That friction is the change of kinetic energy into thermal energy. That's fine. I was having a hard time page turning. Turn page. How do we experience thermal energy in our lives? Yeah, hot. So it's not the same thing as heat. So I'm going to put this little squiggle before. What's a little squiggle probably mean?
Not light.
Yeah, approximately heat. So one of the things we can talk about, sometimes we even call it heat energy, but it's a kind of energy that has to do with heat, and it's kind of like temperature, but not quite temperature. And we'll talk about both of those things in more detail. But you experience thermal energy as heat, or as how hot something is. When the example we've already done is when you rub your little paws, they get warmer, right? You're changing. If you remember, remind me of the energy transfers involved in this. Yeah, so chemical energy in your guns turns to what? No, not yet. Tell me the middle one. Turns to, what is the chemical energy in your guns is causing your arms to move, so that's what kind of energy? Kinetic energy. And then that, when they're in contact with each other, is friction, which generates thermal energy, or which changes to thermal energy. Okay, when we talk about how hot or cold something is, we're specifically talking about the flow of thermal energy, how it moves. We could say I prefer not to say movement, really. I would say flow, because heat is not a substance, but the materials that have thermal energy, that their particles are in motion due to thermal energy, the movement of those particles causes the flow of thermal energy, which we call heat. So if those radiators were on, which they're not, but if the radiators were on, or if we think about the heater in the ceiling, or you think about a fire, the movement of that thermal energy from the source of the heat into your body is what you experience as heat. If you're on a sunny day, if you're sitting there, the movement of the thermal energy from really the sun, from UV radiation, is what you experience as heat. So heat is the flow of thermal energy, and cold is kind of the flow of thermal energy out. What we feel as cold is the thermal energy flowing out from us. I'm going to change what we feel as heat to the flow of thermal energy in. So when the thermal energy is moving into your body, you feel warmer, and when thermal energy is moving out of your body, you feel colder. That's what cold is. Cold, kind of like darkness, is not its own thing. It's the absence of some other thing. Darkness is the absence of light, and cold is the absence of heat, or the lowering of heat. This is nice warm coffee. I have some nice warm coffee here. How does this is kind of just a review of what we just talked about. How does my body perceive this as warm? Why does my body perceive the coffee as warm? No, it's not burning. Okay, so the physical object that is feeling the warmth, this is my tongue and mouth. But why does it feel warm? Because what has greater thermal energy? Oh, I shouldn't have said it like that. How is the thermal energy flowing? Yeah, into me, from the coffee into me, and so I feel as hot. If I had a cold beverage instead, the thermal energy would be flowing from my body into the beverage, and that would feel like cold. So then what is temperature? Do I have a temperature? Does the coffee have a temperature? Yeah, everything we could say has a temperature, but a temperature is the way we do what with heat or with thermal energy? Measure it. Yeah, it's the measure of the average thermal energy of the particles that make it up. The measure of the average thermal energy of particles. So I could have looked it up and I should have probably to get it right, but it doesn't really matter, and it's probably actually better for your privacy that it's wrong. But if I tell you that the average test score on the last test was a 81%, does that mean every single person got an 81%? No, it could mean that, but it doesn't necessarily mean that. Does it mean that anyone got an 81%? It could, but saying that the average of the test scores was 81, does that mean someone had to have had a test score of 81? No, and that's why we talk about temperature as the average, because as you're probably aware, all matter is made of particles called atoms, and those atoms are in constant random motion, and depending on the speed of the particles, the atoms, and the distance between them, I'm going to indicate long arrows are big speed, and short arrows are smaller speeds. So we could say that this material has a particular temperature that is the average of these, even though some of them are moving faster and some of them are moving slower. They don't all have to be moving the same speed to have the same average speed. So temperature is how we measure the speed of these particles. Thermal energy is, you remember that when we were talking about macroscopic, large-scale objects, we said the mechanical energy is an object's potential energy plus its kinetic energy. Well, kind of in the same way for these particles, thermal energy is the kinetic energy plus the potential energy of the particles. And for the particles, unlike it's not gravitational potential energy, this is how far the distance between them. So the faster they move and the farther they are apart, the greater the thermal energy. Does that kind of make sense? The faster they move and the farther they are apart, the greater the thermal energy, and we measure that as temperature. So in what are particles moving faster? A hypothetical cold iced tea that I have, or my warm coffee? Warm coffee. Every single particle is moving faster in the coffee? No, but on average, the particles are moving faster and farther apart in the warm coffee. If we all went on a field trip outside the football field right now, would your body, or the air have greater thermal energy? Or, sorry, greater temperature? Probably your body, because on average the particles would be moving faster and they would be on average farther apart compared to the air. And I corrected myself from temperature because when we say how much thermal energy something has, that's actually a total of all of the motion of the particles, and that's immeasurable. We can't measure that. We'll talk about that when you're in chemistry 2, if you take chemistry 2, but we can't measure how much the total thermal energy of something, because we have to measure the speed and the distance between all the particles, which we can't do. So we usually talk about the temperature. That's how we measure thermal energy, is with temperature instead. There's an equation. Let's talk about the equation we use. I specifically told you there wouldn't be a worksheet for this. You will do math work with this on your chapter review. To me, that will be sufficient. But if you feel like you haven't gotten the practice you need after doing the chapter review, there is a worksheet I could print up, or I could even make one, or I could have the AI make one. This is the equation. I like to write it like this. I think your book writes it M delta T C, but I like this because you can kind of remember it, because this is not an A. I hope you realize this is not an A, but it kind of looks like Q equals M cat. It's not. This is actually the Greek letter delta, but this to me helps me remember it. It might help you remember it, where Q is thermal energy. So even though thermal energy can't be measured directly, as I was just saying, it can be calculated in this way. M is, can you guess? No. Lowercase m is, as it has been before. Yeah, mass. Will we measure mass in the SI? We do use grams, but the base unit is kilograms. Capital C is something called specific heat, which is measured in joules per gram degree Celsius or joules per kilogram degree Celsius. And then delta T, do you remember what delta is from before in the year? It's behind you too. Yeah, who said that? Nice job, Cameron. Change in, what do you think capital T is? No, lowercase t is capital. What? Lowercase t is time. Capital T is temperature. What do you think we measure temperature in the SI? Yeah, degrees Celsius. Degrees Celsius. So if we have, looking at this, if we have a change in temperature in degrees Celsius, specific heat measured in joules per kilogram degree Celsius, and mass measured in kilograms, what do you think we're going to end up with for our unit for thermal energy? So look, the kilograms will reduce to 1 because they're in the numerator here and the denominator here. Degrees Celsius will reduce to 1 because they're in the numerator here and in the denominator here. So we're going to be left with joules. Does it make sense that we would measure thermal energy in joules? Does it make sense that we would measure energy in joules? Yeah, that's what we've been measuring energy in. So we can calculate the amount of thermal energy in something by multiplying its mass times its specific heat times how much its temperature has changed. But you'll recognize, in order for this to work, the temperature has to have changed. We can't just measure the thermal energy of something. We can't just be like, I'm going to measure the thermal energy of this coffee. We can only measure it as the temperature changes. So either as it's heating up or cooling down. It has to, if the temperature change here is 0, thermal energy is 0. Because we're not actually measuring the amount of thermal energy, as I was saying. We're measuring how much thermal energy has been gained or lost. And maybe I'll put that. Thermal energy gained or lost. How much the thermal energy has changed. In the English system, as a kind of a side note, I think your book might talk about this too, but as a side note, in the English system, we measure thermal energy in calories. And that's also, you'll recognize how we measure food energy. How much energy food gives us is measured in calories, and that's because of this equation. In fact, you can see here the objective for my Chemistry 2 class right now, they're doing thermochemistry. The next lab they're going to do is they are burning a chip, like a potato chip, with fire, and they're measuring how much it heats up some water. So they're going to burn the potato chip in a little bowl, measure how much it heats up some water, and then using this equation, which is a pretty simple equation, they can see how many calories that chip had in it. And they're going to compare that to the amount of calories the bag says it has. Because that's really, basically what your body is a fire, a slow burning fire that does the chemical reaction of burning as calories in order to give you energy. Speaking of our objective was investigate systems of thermal phenomena. Investigate systems of thermal phenomena. Let's write that down. And I'll give you an example of that here in a second. Investigate systems of thermal phenomena. Investigate systems of thermal phenomena. Another side note, someone said earlier today, what's a phenomenon? Phenomenon is just a thing that happens in nature. I'm surprised I haven't used that word in your presence before, or that I haven't explained that to you, but a phenomenon is just a thing that happens in nature. One kind of thermal phenomenon is that there are 3 ways heat is transferred. Remember, heat is itself the transfer of thermal energy, but I think it just sounds like better English to say heat is transferred than to say heat occurs. But there are 3 thermal phenomenon that occur in the universe. They're all vocab words, and so you should know all of them. Can you give me an example of how heat is transferred, how thermal energy moves from one place to another in the universe? Give me an example. Conduction. Yep. Conduction is one. Explain conduction to me. I want you to explain it to me, not what you wrote down in your vocab, which is right from the book. So you can read what you wrote for your vocab, but tell me what conduction is.
It's like heat absorbing.
Okay, yeah. Heat transferred by, you said absorbing. Someone just said heat transferred by what? What do the objects have to be doing for conduction to work? Yeah. by direct contact. I'm going to put that. I think that sounds more scientific than touching, but by direct contact. So a hot object in contact with a cooler object, the heat will move from hey, fill that in. If we have a hot object touching a cool object, how will the heat flow? From hot to cool. That's one of the laws of thermodynamics, that heat will always flow from hot to cool, or from warmer to cooler. If we open the window, it will feel to you like cold is coming in. But what's actually happening is heat is flowing out. The heat from the room is flowing out into the rest of the environment. Does that kind of make sense? Heat is always flowing from warm to cool. Okay, what's another kind of heat transfer? Maybe I'll write what I just said down. That is pretty important. Heat moves from warm to cool. I believe that's I'm not going to say, actually, it might be the third law of thermodynamics, but I was going to say, but I don't actually know, so I'm not going to say. But heat moves from warm to cool. Okay, what's another way that heat flows? Convection. I meant to turn on my lava lamp this morning too, but I didn't do that. But there's a picture of a lava lamp, and you've seen lava lamps before. Convection, explain convection to me from your vocab. I mean, use it in your own words, but use your vocab. What do you think?
Transfer thermal energy.
Yeah, the key word there is it's in a fluid. So fluid motion. No, I'm going to put fluid moving due to thermal energy. Have you seen a lava lamp in action before? This one's not on, so it's not gonna. You're just gonna have to imagine that it is. But I'm gonna bring my lava lamp over here. I'm gonna leave his little hat on because he looks and feels gross without his hat. So this is a lava lamp, and it's off. I have it out here in the wild. Where would the heat source be in this lava lamp generally? Yeah, under it, and it takes the place of a light bulb, right? So there's heat below it, and convection is that heat. You might have heard someone in your life say that heat goes up or heat moves up. Heat itself doesn't always go up, but warm fluids rise. That's what it is. You might have heard heat rises, but it's actually that warm fluids rise. And so a fluid in science, in medicine or in your daily life, a fluid is probably specifically something you drink, like it's a liquid that you drink. But in science or in the physical sciences, a fluid is any object or any substance that can flow. And so in science, that is in the physical sciences, both gases and liquids count as fluids. And so in this, which is full of a liquid, as it heats up down here, this wax melts and it becomes a liquid, okay? And then that liquid becomes warmer and therefore less dense. And when it's less dense, it floats. And when it's up here, it becomes cooler and more dense. And so it sinks. And that pattern continues. I'm going to turn it on now, even though it's too late. That pattern continues and continues and continues, and that is convection. And so I'm going to diagram that here. So here I have my very well drawn, I must say, lava lamp, and mine's blue with yellow inside of it, but the yellow's kind of hard to see, so I'm going to put orange. So it gets warmer, becomes less dense, and rises to the top. And then up here it gets cooler, becomes more dense, and sinks down to the bottom. And this kind of concentric or circular motion is called convection. And that happens in any fluid. What's at your school or your home, what's that building full of? Like all this stuff. You might say, oh, it's an empty room, but it's not empty. What's in here? Air, which is a fluid. And so at your house, it's not that heat rises, but since we are creatures that live in the medium of air, the air, when it gets warmer, becomes less dense and floats to the top. And then there it becomes cooler and sinks to the bottom. At our house, we have a 2-story house, and at our house, when it's wintertime, we keep the heater vents open on the first floor and we close them on the second floor, because the heat then will come out more on the first floor, where it will rise and the second floor will become warmer. In general, this is true in this building, depending on how the heating is set up, but in general, the second or third or fourth or whatever floor of a building will be warmer than the bottom floors because of convection. Okay, what's another kind of heat transfer? Radiation. Now, some of us might wish that there was a slightly different word for this, because it reminds a person of nuclear radiation, which is a whole separate thing. We will talk about nuclear radiation later in the year. But both of those have to do with the prefix radi, or radius, which you remember from a circle. What's the radius? It's half of the diameter. Yeah, but it's a line segment from the center of the circle outward, right? That's what a radius is. And so radiation is energy or heat flowing from the center of an object out. Now what have I drawn? What does it look like I've drawn? The Earth exploding. No, for those of us who aren't so into the apocalypse, it kind of looks like I've drawn the sun, and the sun is our major source of radiation. So energy, so thermal energy, let's this one. Thermal energy flowing out from a central source. What's a radiator? There are a couple different kinds. So that heating device in this room is a radiator. How do you think the heat flows from the radiator? The radiator itself gets super hot, and what? It does not explode. I really, really, really hope it doesn't explode. The radiator itself gets really hot, and the heat energy radiates out from that point. Now, with a radiator, with the device called a radiator, there's also definitely going to be some convection, and if I touch it, definitely some conduction, or if anything touches it, definitely some conduction. But it primarily is radiating out heat. Heat is coming from a central source and moving outward. What else is a radiator?
Tractor.
Okay, yeah, true. So we'll pretend this is a tractor. Yeah, there's this thing on the front of it's on the front of a real car too, but it's also on the front of this fake car. It's on the front of an old-timey car. It's kind of how I drew it so you can see it better. But basically, the engine, which is here, gets hot. Whoo, it's a hot engine. And so that engine, because it's touching the radiator, conducts. It also has all kinds, in a modern vehicle, has all kinds of fluid-filled hoses that carry heat energy away from the engine and out through the radiator. The modern radiator is full of something called radiator fluid and has a little cap on the top that if you open it, you'll get burns all over you when it's running, because, and Joe has experience with this, is what he's leading me to believe, because the point of this is that it gets super hot. Now back to our equation. Water, or even better, radiator fluid, has a very high C, a very high specific heat. It takes a lot of energy for it to change temperature. That's what specific heat is. It takes a lot of energy for it to change temperature, but it does change temperature. And so it can absorb a lot of heat energy from the engine and radiate it out to the environment. Cars generally run better the colder it is. The colder it is outside, the more effective the radiator is at removing heat, because heat moves from warm to cool. If it's hot outside, the heat doesn't flow as much from a hot environment to a warm environment. It flows a lot more quickly from a hot environment, the engine, to a cool environment outside. Do you have questions? Your book goes on to talk about how heat can be used for work, which I will trust you to read about. But it basically comes down to kind of what we talked about, the engine. It talks about the internal combustion engine. It talks about refrigerator, a refrigerant, which is kind of like what a radiator is a refrigerator. It radiates, it takes heat from a certain place and radiates it out in some other environment. But do you have questions about the ways that heat is transferred, or primarily about the systems of thermal phenomenon, the ways that heat moves? Do you have questions about this equation? We'll do more practice with the equation. I got to pick my marker up. I got to pick my book up. I gotta pick my coffee cup up. Turn off the light, please.